Welcome back, ladies and gentlemen. We are opening up a new section here, and the goal of this section will be able to use characteristics of perpendicular and angle bisectors to find missing side lengths and angle measures. Specifically in this video, we are going to define what a perpendicular bisector is, and we are going to go ahead and define and utilize the perpendicular bisector theorem as well as its converse to go ahead and find some missing side lengths. So let's dive right on in. First and foremost, let's kind of just recap of what it means to be a perpendicular bisector. Remember, it is a segment, all right, that is both perpendicular and bisects it. So that means it's perpendicular and it goes through the segment's midpoint of one another, right? And so here's a prime example. So we have CP, the line, is perpendicular to AB, the segment, but since these two congruency tick marks show that they are the same on both sides, that means that P is the midpoint of the segment AB. We would also call this equidistant, right? This is a big term that we're going to be using for the rest of the year. Equidistant. From A to P and B to P is equidistant. They are the same distance from a particular point, all right? Equidistant. So what is the perpendicular bisector theorem? Well, what we're saying here, guys, is that, hey, if we have a segment, AB, and we have a line that is the perpendicular bisector, the distance from any point that is not on AB, but that is on CP, is equidistant to both of the endpoints of the segments. So C is equidistant to A, C is equidistant to B. But if I had a point down here, let's call it D, this point D would be equidistant to B and equidistant to A as well too. So we're saying that any point that lies on the perpendicular bisector is equidistant to the two endpoints. The converse holds true as well. Then we're saying if a point is equidistant from the endpoints of a segment, then it actually is on the perpendicular bisector. So let's just say, for example, here we have this point D that we have down here in the distance, right? Right now you see D is off of line CP because there's a question mark. We're wondering, is D actually on the perpendicular bisector? Well, since DA is congruent to DB, yes, I can claim that D is on the perpendicular bisector. And it's almost like I can just extend the line to go through D, right? I can extend the line to go through D, and it almost could rename it CD if I really wanted to for that perpendicular bisector. So let's use this in some application. So it says find each measure. We want to find what the measure of RS is. Well, let's kind of just go through here real quick. What do we see? Well, we see that it is perpendicular, our QS is perpendicular to RP, and it's a bisector because of these two tick marks, meaning Q is the midpoint. Well, if that's the case, any point that is on the perpendicular bisector is equidistant to the two endpoints, thus meaning that we end up seeing that we've got SR and SP being congruent, meaning this also equals 6.8. All right, well then down here we say, hey, what's the measure of EG, the whole segment EG? Well, if this is 24 and this is 24 and this is a right angle, the only way this works is if FH actually is the perpendicular bisector. So right now we see that it is perpendicular, but we can claim it a perpendicular bisector by the perpendicular bisector converse. Since 24 is congruent to 24, they are equidistant to the endpoints, thus making EF 9.5 as well. Well, if EF is 9.5, EG is 9.5 times 2. So 9.5 times 2, 18 and 1 ends up giving us 19 there. What about one more in some application using some algebraic expressions? Let's find the measure of AD. Well, the measure of AD is, of course, right here. And again, I know that BD is a perpendicular bisector because of the right angle and the two congruency tick marks, thus making AD and CD congruent as well. D to C is equidistant to D to A. So I can set up an equation that says that 3x plus 14 is equal to 5x because they are equidistant. 14 equals 2x, and x equals 7. So 5 times 7 after I substitute means that AD has a value of 35. All right, and so that is our perpendicular bisector theorem and its converse.